So our next speaker is Boxy Lee. Boxy is a master student at ETH Zurich, but currently he has exchanged at TU Delft. And he's one of the developers behind the QuTiP project, which is an essential software toolbox for quantum simulations, including noisy and open quantum systems. And today he's going to be talking about the outcome of his Google Summer of Code project in a talk titled Simulating Noisy Quantum Devices with QuTiP.
Hello, can you hear me? Good? Yeah. Thanks for the introduction. So my name is Boxy. I am a Google Summer of Code student last year, and that's when I joined the QuTiP community for this project. So in this talk, I'm going to talk about a new module in QuTiP that is going to help you simulate your quantum chips, your quantum system. Now, if you were here last year, you might already heard a talk about QuTiP, which was the general QuTiP stuff given by Shanawat. Now, in this talk, we'll focus on this new module. So I'll first still give a very brief introduction of QuTiP, but only the very central part. And then we'll come into this new simulator. Yeah, so to begin with, so today we have a lot of different approaches that are trying to build us quantum computers. So we have superconducting system, quantum dots, or some photonic platforms, also ion traps. They are all different kind of platforms. But in your quantum chips, or what you have in your system, is usually a very small quantum system that we treat them as qubits. Because everything here is quantum, that's why I want to use them, there's a lot of counterintuitive phenomena happening there. So one way of understanding your quantum system and study what is really happening in your chips is by simulation. So QuTiP, as the name indicated, the quantum toolbox in Python, is exactly this Python package that helps you to understand your quantum system. We have a lot of different nice tools in our package, ranging from some nice abstraction of quantum operators. We call it QObject. So we have a lot of transformation function, which can transform between, for example, Troy operator or super operator, which are commonly used in quantum information theory. On the other hand, we also have many predefined quantum states that can help you to, for example, set up your quantum simulation. And we also have nice visualization tools. So like block sphere or Wigner function used in optical system. So they will help you like have a closer look or more intuitive understand of your quantum system. But those are very nice tools. We have many tons of them. Now, the central part that combines them and unites them together is actually the quantum dynamics solver of QuTiP. So don't freak out. This is the only page with formulas. Now, what I want to say is that despite this eccentric behavior of quantum physics, we can still describe things with physical laws. So the Newton equation in the quantum world will be the so-called Schrödinger equation. It basically means that if you gave your initial state, and then you gave something called the Hamiltonian, which basically determines the dynamic of the system, and then you can actually calculate what kind of state am I having in the future. Now, of course, it's never going to tell you what exactly is the measurement result, because we still have this uncertainty, but it can describe your state, your physical system, in a statistical way. Now, this works only for a perfect isolated system. But in reality, it's never the case. So we're trying very hard to isolate our quantum system, like we put it in vacuum chamber, or we cool the temperature down to some millikelvin, but still there's always an environment around. And this environment will lead to something called decoherence. So if you store your qubits in some quantum memory, and you come back, like after a microsecond or millisecond, you measure it again, then probably you find out that the state changed. It dropped from some state 1 to state 0. So it means that your quantum system actually talks to the environment. So this kind of dissipative behavior is captured by the so-called Lindblad master equation. And the solver of this equation is the central part of QuTiP. So we also have a bunch of other solvers. Some of them deal with a slightly different situation, like if you have some invariance in your system, but they are basically all designed and used for study quantum dynamics. So based on all those solvers, a lot of physics phenomena can be studied, like quantum optics, cavity QED, quantum optimal control, and also the topic today, quantum information processing. Now, when we talk about quantum information processing, we usually use this circuit model. So QuTiP also have this very nice quantum circuit representation where you can create a circuit, you can add gate to it. So we have a lot of predefined quantum gates, and we also allow you to define your gates, your customized gates, your own gates in a matrix form. So when you run the gates, you get the final state by matrix production. But this part is not new. Like, you might also ask that we already have many other softwares that are doing this quantum circuit simulation. So we have QuiZKit, Project Q, and dozens of others. So what's the difference? Now, the difference here is that in QuTiP, we are going to simulate the circuit at the level of your physics dynamics control pulse. So we will first transfer the quantum circuit into the control pulse of a device, of a physics system, and then we simulate the physics dynamics. So our simulation is running one level lower than the circuit model. So with this, I'll go to the second part, so noisy device simulation, this new module in QuTiP. Now, imagine you have some quantum chip. And usually, the way you want to control your qubits is through some control pulse. So you either shine a laser on it, or you give it some microwave signal. So this kind of your quantum chip is represented in our simulator in a class called processor. So it has information like the number of qubits, the typical relaxation time, T1, T2, and also the most important, your control pulses. So the control pulses is actually the basic element in our simulation. So it's characterized by the Hamiltonian, which describes the interaction, and the target qubits, and also the pulse coefficients and the time sequence. So basically the last two here describes what kind of shape your pulse is going to have. So when do I want to turn the pulse on, and does it have a rectangular shape or triangular or even a Gaussian shape? So with this, you can define your device and add some pulse to it. Like I show here a short code block. You have sigma Hamiltonian and act on qubit 0 with some pulse shape. And then you click run, you run the states. Our simulator will tell you what does your state looks like at some future time t. So this is less interesting if we are really interested in the ideal case, because if we want to simulate ideal gate, then why don't just use the matrix? Now, things become interesting if we want to add noise. So usually in those gate-based simulator, the way of simulating noise is, for example, through some depolarizing channel. We assume that a small part information of my quantum system is lost after each gate, or you say that I apply some flip error with some probability p after each gate. But there's always an additional level of abstraction there. So you have to calculate with which probability do I want to apply this error gate. So in our case, because we are doing this simulation at the physics level, you don't need to worry this. So because we have an open system solver, it is quite natural to add like single qubit relaxation noise. But beyond that, you can define a lot of other kind of noise, like pulse shift noise, where your pulse is suffered from some random amplitude noise, or maybe you have exponential tail. Or for example, it can happen that your pulse is not very well focused. So you're trying to address one qubit, but because the pulse is a little bit broadened, you address actually several neighboring qubits at the same time. There's also this so-called leakage noise, where, so basically we always imagine our qubits to be a two-level system. That's why I call it bit. But in fact, even in a simple atom, there's infinite many energy levels. So we just pick two of them to use them as our qubit. But if your control pulse is not perfect, which is usually the case, it's very likely that you can also excite your state to some third level that is not even captured in your qubit description. So in our simulation, you can easily define or characterize those kind of noise by, for example, some ancillary level. So basically, your qubit circuit is still a qubit, but when you run simulation, it actually runs on a three-level system. Now, with this pulse level control and noise, you can basically characterize your chip. But then the part that connects the quantum circuit and the physics dynamics is what we call backend and compiler. So this part is still under active development, where we aim at create different backend compilers for different common physics systems, like those that are commonly used for quantum computing. So basically, what a backend does, in our sense, is that you give it a parameter, a few parameters, like number of qubits, or the frequency of my resonator, or the frequency of my ion trap, and then we construct the control Hamiltonians for you automatically. So yeah, basically it's a simulator. Be careful, it's still a simulator, so there's no hardware backend. We're just simulating different kind of physics system. Now, on the other hand, the compiler starts from the quantum circuit and find the corresponding control pulse that realizes circuit. So with the help of those two, you can basically describe your quantum device with a few parameters, and then you can load some quantum circuit defined in QuTiP, for example, QuTiP circuit module, and then you add some noise to it, you run the simulation, and you can see how does this circuit perform on this certain device, maybe even with some additional noise. So in a more illustrative way, here is a figure for the workflow. So basically what you can do is that you choose some predefined backend and compiler, and you give your quantum circuit as input. So the compiler will then transfer your circuit into the ideal control pulse of this certain device. And then the noise object will add noise to those control pulse. So you can have here, for example, phase pulse shape noise, or some additional noisy signal. We then patch all those things together, create a physics model around it, and send it to the QuTiP solver. So the solver will show you how the system looks like as a function of time. So as an example, we have a simple Deutsch-Jozsa algorithm implemented on our tutorial page. So tutorials in the form of Jupyter Notebook. You can you can read the instruction and also run the code by yourself at the same time. So we have a very simple Deutsch-Jozsa circuit here of 3 qubits, and we find the control pulse of this algorithm on one called spin chain model. So each color here in this figure represents a different control Hamiltonian, basically a different control pulse, and those control pulses will realize this circuit. So those higher pulse is for S0, and those ones are for the C0 gate. So in the notebook, you can find that we run the circuit and compare the results with and without some additional noise. The summary. So in this new module, we produce a structured framework that can help you to simulate your quantum device. So we offer this pulse level control interface, and with this with this way of defining noise, you can actually simulate your device in a more way closer to physics. So we will transfer the gate into the control pulse, also a noise to it. With the help of backend and compiler, you can actually set up your device, a simulator of a device, with a few lines of code. So there's a lot of potential use cases for this. So for example, because we are now running a simulation, you can actually turn on and turn off noise. It means that I can compare the influence of different kinds of noise. So in this way, you can actually determine, or at least study, get an intuition, what is actually the dominant noise in my system. If you are design a quantum algorithm, you can also give your quantum algorithm as an input to our system, and then you can see that how does the algorithm perform on a certain kind of device, or is my algorithm sensitive to some certain kind of noise. So in addition, you can also use it to, for example, test some noise mitigation scheme. So there's a paper from IBM where they use this extrapolation to mitigate noise. Basically, what they do is that they have a parameter that characterizes the strength of noise, and they run their device, a real physical device, for different noise strengths. And they extrapolate back to find, okay, what does the result looks like if I have no noise. So because the argument is basically at the level of Hamiltonian, and this module will be useful to, for example, verification their results, or maybe even do some improvement. Now with this, I'll go to the end of my talk. So those are the developers for QuTiP. So because QuTiP is actually already 8 or 9 years old, there has been different generations of developers. So those two are the original developer from Japan. And so they have nice paper published. So if you are using QuTiP for your research, please also cite us. And those are the current lead developers. You can see that we have people from basically all around the world, from Europe, from Canada, from Japan. And we also have dozens of other contributors who contribute to the QuTiP project. So if you are interested in this project or in general in QuTiP, you are very welcome to visit our website, and we have tutorials in form of Jupyter notebooks. So there's also a few tutorials about this project, and you can find them on our tutorial webpage. We also have documentations for user guide and API, and also if you are interested in the code, welcome to go to our GitHub page. And if you find some bugs or maybe even typos in documentation, you are very welcome to point it out to help us improve things. And also, you can also contribute your own code and let it become part of QuTiP. So another very nice way of contributing and become one of the community is through the GoGo Summer of Code. So this year we are participating again in GoGo Summer of Code. So between May and August. So if you are about to graduate in a few months, or you are going to have a very long holiday, it's a very nice way to join the team. So you can find a few projects proposed on this page, a few more is to come. And you are also very welcome to bring your own project. So what you want to do with QuTiP, or what you want to add to QuTiP. So because I am a student of last year, I very highly recommend it if you are interested in open software development. So even if you have zero experience, it's also okay because you are going to be mentored by the QuTiP members, both from the coding side and from the physics side. So, and also Google will give you a scholarship for a few months for support. And so this is my blog of last year. So where I wrote some of our ideas and what the problem we're trying to solve, and also some of kind of our method we used. And at the very end, a small advertisement for myself. So I'm a master student that is about to graduate this summer and looking for PhD positions. So if any of you have some nice projects and find my background might be helpful, please contact me. Okay, with this, I'll thank you for your attention. Thank you very much. Yeah.
Are there any questions?
Yeah.
One sec.
Hi, what format are the control pulses emitted in the backend of QuTiP? Is it like splines, frequency domain, time domain?
Sorry?
The control pulses that the backend emits that are device specific, what's the format or how are they represented? Is it like splines or frequency domain or?
It's basically just as a figure I showed before, the control Hamiltonian form. So we don't yet have a backend for ion trap design yet. It's still in development. But basically, what it consists of is the Hamiltonian, corresponding Hamiltonian, the target pulse, and that will characterize your device.
Okay, cool. Thank
you.
you.
Yeah. Yeah.
Okay, so you were talking about the different noises.
Yeah.
What happens if in your gate, if you have some structure defect or surface defect, did you do such study? Like, will it modify or distort your output pulse?
It basically determines, so this part will come into the backend. So now we only have backend for a very limited range of devices. And I think those like defect you mentioned will be very small part like in the device and can be maybe modified how the evolution is running backend. You can do that, but it will depend very highly on what kind of system it is, right?
Okay, we got time for one more.
Hi, I was wondering, this solving of the differential equation, is this just cutting it up in very small time steps and just running through it, or is there something more clever happening in the background?
There are different approaches. So there is differential equation approach. You use something similar to doing QuTiP, not exactly, and solve it. And there's also the Monte Carlo approach. So you basically build different sample thousand of approaches with different kind of collapse operator, Lindblad operator, and then you take the average of different Monte Carlo trace. That's a typical way to do this, like in quantum optics and this field. Yeah.
Okay, so let's thank Boxy one more time.